Hi, I'm Tali, and we've made a breakthrough in tokenization performance. We have achieved gigabyte tokenization on consumer desktop CPUs with sub-millisecond latencies. It's a 10x increase in throughput, and P99 latency numbers half that of others' best runs. And the best part about this is it's a drop-in replacement for your existing Python, Node, and Rust tokenizers. So let's look at how we measure what the numbers are and how much this impacts your pipeline. For our benchmarks, we measure from entering the function, results being returned, and then finally enumerating the results. By walking through every token, we ensure lazy evaluation, iteration cost, and language overhead are included. We only present on this end-to-end number as it's closer to what you will really experience. For latency, we want to focus on the fixed overhead of each call. So we use a small workload with a large number of executions. We do one warm-up and 1,000 timed runs. From the results, we get median and P99 latency in milliseconds. This shows the typical experience and worst-case experience users actually feel. For throughput, we want to focus on the input for each call because that is what varies. So we use a large workload with few executions. We do one warm-up and 3 timed runs. From the results, we get throughput in megabytes per second, which tells us how long it should take to process an input of a given size. There is a large combination of benchmarks to run, and we need to run them multiple times. There's also a large gap between the slowest and fastest tokenizers. So to be practical, we bucketed tokenizer methods into 4 speed tiers. Each tier runs different size tests to keep the execution times reasonable. The faster the tokenizer, the more work you need to provide it to hit peak speeds. We use the O200K model for comparison as it's the most widely supported model for tokenizers. We have published all of our benchmark results in detail on a Hugging Face tokenizer leaderboard. This allows you to interactively explore the data. Python does not have to mean slow tokenization. If you minimize object churn and keep the hot path inside optimized native code, you can still get very high throughput and sub-millisecond latency. For example, we use number to make the iteration of tokens fast in the benchmarks. If we use native Python to do this, we would see the end-to-end numbers drop to around 400 megabytes per second. For our tokenizer, we have Python binding to a Rust implementation. We also provide NumPy, Arrow, and Polaris API convenience integrations. On O200K, it is about 19 times faster than the next fastest tokenizer, and it gets down to 0.34 milliseconds for P99 latency. Let's look at the Python performance of our tokenizer on other models. R50K had the best performance, and Qwen 3.5 was the slowest for throughput. For latency, we see that CL100K has the highest latency, which was a bit unexpected, and we ran the test a few times. Llama 3 had the lowest P99 latency, and R50K had the lowest median latency. For Node, we need to take the same approach as Python. There is not a number equivalent, so we create a Rust enumerator and counter that can be called from Node. If we use native code to do this, we would see the end-to-end numbers drop to around 500 megabytes a second. For our tokenizer, we have Node binding to a Rust implementation. On O200K, it is about 9.5 times the next fastest Node tokenizer, and it gets down to 0.4 milliseconds at P99 latency. Let's look at the Node performance of our tokenizer on other models. For throughput, R50K had the fastest results and Gemma 3 has the slowest. For latency, we see that Qwen 3.5 has the highest latency and Llama 3 has the lowest. The benefits of a language like Rust really show when running code in a tight loop, which is the tokenization use case. We hit gigabyte speeds on the benchmarks. On O200K, it is about 9.5 times the next fastest Rust tokenizer, and it gets down to 0.23 milliseconds for P99 latency. In the quest for performance, We even created a CUDA implementation. But for the type of problem and the overhead of transferring between host and device, the speeds were only 500 megabytes a second with P99 latencies of 30 milliseconds on our RTX 4090. Let's look at the Rust performance of our tokenizer on other models. For throughput, R50K had the fastest performance and O200K was the slowest. For latency, we see that Gemma 4 has the highest latency. Tekken and Llama 4 tie for the lowest. So, if you're looking to make meaningful gains on your end-to-end workloads by 10xing your tokenization performance, please contact us or see our website for more information.